Revolutionizing particle physics. CU Denver's miniature chip for extreme electromagnetic fields. Imagine being able to unlock the kinds of extreme electromagnetic fields once thought exclusive to massive scientific facilities, right from a device you could hold in your hand. That's exactly what a team of engineers at the University of Colorado Denver, under the leadership of Aakash Sahai, have achieved in a breakthrough that's turning heads across the scientific community. But here's where the story gets even more intriguing. Their innovation now challenges the very scale and cost assumptions of high-energy physics, possibly reshaping research for decades to come. The newly developed silicon-based chip is not your average piece of tech. Previously, scientists needed enormous structures like the Large Hadron Collider at CERN to create the kind of extreme electromagnetic fields required for cutting-edge experiments with fundamental particles. With this chip, roughly the size of a thumb, those same fields can now be generated in much smaller, more accessible settings. How's this possible? The device harnesses the rapid oscillation of electrons within silicon, producing powerful fields while also expertly managing the significant heat and energy such processes unleash. Unsurprisingly, this leap has already earned provisional patent recognition both in the United States and internationally, cementing its place as a standout in scientific innovation. The chip's development wasn't a solo act. Design and refinement happened at CU Denver, with vital testing support from the SLAC National Accelerator Laboratory, showcasing the power of collaboration in pushing the boundaries of what's possible. And this is the part most people miss: the chip's resilience. Not only can it handle the impacts and energy flows of high-energy particle beams, but it also remains structurally sound during these intense processes. This ability is central, as it means future particle colliders and research equipment could be scaled down dramatically, potentially democratizing access to discoveries once reserved for a handful of government-funded labs. The potential uses for this technology stretch far beyond pure physics. In the quest to uncover the secrets of the universe, like the elusive dark matter, the generation of such intense electromagnetic fields is essential. Could this chip help unlock new chapters in our understanding of everything from unseen cosmic materials to the very structure of reality? Some researchers think so. Moreover, this technology may lead to the creation of gamma-ray lasers with the astonishing ability to image tissues at the atomic scale, driving advances both in science and medicine. For example, these lasers could pave the way for unprecedented cancer therapies, with treatments precisely targeting cells at the nanoscale. Are we on the verge of a revolution in both diagnostics and oncology? But the story doesn't end there. Sahai and his colleagues believe their silicon chip innovation could even enable new tests of the fundamental laws of nature, possibly probing ideas as grand and controversial as the existence of a multiverse or the intricate fabric of space-time itself. To understand where this breakthrough came from, it's worth noting Aakash Sahai's extensive background. His pioneering work began in 2018 with research exploring antimatter accelerators. With a PhD in plasma physics from Duke University and experience at internationally renowned institutions like Imperial College London and Stanford, Sahai brings unique depth to this project. The collaborative aspect is further highlighted by the involvement of Kalyan Tirumalassetti, a graduate student at CU Denver working on advanced degrees in electrical engineering, underscoring just how interdisciplinary this work really is. There's also a powerful economic dimension to this story. The University of Colorado Denver's broad research initiatives, including this one, generate an estimated $800 million annual impact for the state's economy, a reminder that fundamental science often fuels real-world progress. Here's a point for debate. Will innovations like this chip truly democratize advanced scientific research, or will barriers in cost, training, and ethical use persist? What about the potential for dual use in controversial areas like surveillance or military technology? Should there be checks? Where do you stand? Are you excited by the promise of making advanced science more accessible, or concerned about unforeseen consequences? Let's talk about it in the comments. Breakthrough in extreme plasmons. Unlocking gamma-ray lasers and multiverse probes. Imagine a world where gamma-ray lasers and probes for the multiverse are no longer just science fiction. A groundbreaking development by a University of Colorado Denver engineer is turning this fantasy into a probable reality. This quantum tool, leveraging extreme plasmons, could pave the way for futuristic technologies that were once confined to the realms of sci-fi. Dr. Aakash Sahai, an assistant professor of electrical engineering at UC Denver, believes his discovery could be as transformative as past materials science breakthroughs that led to lasers, computer chips, and LEDs. This innovation aligns with those historic advancements, Sahai asserts. It's thrilling because it will unlock new areas of research and directly impact our world. The power of extreme plasmons and electromagnetic fields. When engineers need to generate ultra-high energy electrical fields for experiments, from medical applications to probing the essence of reality, they typically rely on massive facilities like CERN's Large Hadron Collider, famous for discovering the Higgs boson. However, exciting electrons in materials to create such fields is a significant challenge. Now, Professor Sahai has devised a novel technique to produce these extreme electromagnetic fields in a lab setting. Sahai's method, detailed in advanced quantum technology, involves creating a silicon-based chip-like material with unique properties. Thanks to extreme plasmons, this material can withstand high-energy particle beams, manage energy flow, and allow scientists to access electromagnetic fields generated by quantum electron gas oscillations, all within a space as small as a thumb. Because extreme plasmons help manage the heat from electron oscillations, samples used in high-energy experiments remain stable. This newfound material stability offers scientists a powerful new tool, potentially shrinking massive colliders into a chip-sized device. A glimpse into the future, from cancer treatment to multiverse exploration. While practical applications are still years away, Sahai envisions advanced technologies becoming feasible. Gamma-ray lasers could become a reality, he says. We could achieve imaging at the atomic nucleus level, enabling real-time observation of nuclear processes and leading to better medical treatments and cures. The most futuristic application proposed by Sahai and his graduate student, Kalyan Tirumalassetti, is using extreme plasmons to probe the fabric of reality. This technique could test theories about our universe, including the possibility of a multiverse. To understand nature at the most fundamental level is crucial, Tirumalassetti emphasizes. Engineers provide scientists with tools to not just understand, but also innovate, and that's exhilarating. The team plans to refine their silicon chip material and improve testing techniques over the summer. Although perfection may take time, their discovery has already excited the quantum community for its potential to revolutionize physics, chemistry, and medicine. It's going to take a while, but within my lifetime, it is very probable, Sahai concludes. Christopher Plain, a science fiction and fantasy novelist and head science writer at The Debrief, invites you to follow him on X, explore his books at plainfiction.com, or email him directly at christopher@thedebrief.org. But here's where it gets controversial. Are we ready for the ethical implications of such powerful technologies? And this is the part most people miss. How will these advancements reshape our understanding of the universe? Share your thoughts in the comments. Are you excited or apprehensive about this future? Revolutionary quantum tool developed at CU Denver, a game changer for science. Imagine a world where cancer cells can be eliminated without harming healthy tissue, and where the very fabric of the universe is revealed, potentially proving Stephen Hawking's multiverse theory. This isn't science fiction. It's the groundbreaking work of an engineer at the University of Colorado Denver. Assistant Professor of Electrical Engineering, Aakash Sahai, PhD, is developing a tool that could revolutionize the future of science. His work was recently featured as the cover story in Advanced Quantum Technologies, a leading journal in quantum science, materials, and technology. This technology will open up entirely new fields of study and have a direct impact on the world, Sahai enthusiastically shared. He draws parallels to past technological breakthroughs, such as the discovery of subatomic structures, leading to innovations like lasers, computer chips, and LEDs. Sahai's innovation, rooted in material science, follows a similar trajectory. But here's where it gets controversial. Sahai has found a way to create extreme electromagnetic fields never before seen in a lab. These fields are generated by the rapid vibrations and oscillations of electrons in materials, which can power everything from computer chips to superparticle colliders searching for dark matter. Before this discovery, creating such strong fields required massive, expensive facilities, like the 16.7-mile-long Large Hadron Collider at CERN in Switzerland. Sahai's breakthrough involves a silicon-based, chip-like material that can withstand high-energy particle beams, manage energy flow, and allow scientists to access electromagnetic fields created by the oscillations of the quantum electron gas. This advancement could replicate the results of a miles-long collider into a chip about the size of a thumb. This breakthrough in technology can make a real change in the world. It is about understanding how nature works and using that knowledge to make a positive impact on the world, said Kalyan Tirumalastedi, a graduate student working on the project. CU Denver has already applied for and received provisional patents for the technology in the United States and internationally. While real-world applications are still years away, the researchers plan to continue developing the technology at the SLAC National Accelerator Laboratory, a facility operated by Stanford University and funded by the U.S. Department of Energy. Gamma-ray lasers could become a reality, Sahai envisioned. We could get imaging of tissue down to not just the nucleus of cells, but down to the nucleus of the underlying atoms. That means scientists and doctors would be able to see what's going on at the nuclear level, potentially accelerating our understanding of immense forces at such small scales and leading to better medical treatments and cures. Eventually, we could develop gamma-ray lasers to modify the nucleus and remove cancer cells at the nano level. And this is the part most people miss. The potential for this technology extends far beyond medical applications. It could revolutionize fields like quantum computing, material science, and even our understanding of the universe itself. In the immediate future, Sahai and his team will refine the technology that has been in development since 2018. But what do you think? Could this breakthrough truly revolutionize science as we know it? Or are there hidden challenges we haven't considered? Share your thoughts in the comments below.